Let's just go over the types of discontinuities. Uh, this is discontinuous because it has the hole right there. But the limit does exist. If I want to talk about it, the limit exists no matter what. But so, and this can be fixed. This discontinuity can be fixed by just defining it there. So this is a whole discontinuity. It is removable discontinuity, meaning that you can fix that problem by defining it. Kind of like in a road, you're on a road and you got a pothole. What do? They fill it in, no? And they fix it, don't they? Kind of the same idea. You can fix that one maybe. All right. For that particular one. This one has a vertical asymptote at x equal to 0. This is not fixable at all. This discontinuity, number 2, discontinuity due to a vertical asymptote. This is a little extra to talk about. I don't have it here, but I'm going to say that it is discontinuous on R. Also, let's go with this. Say that it is discontinuous on R. And R is all the on the reals. It's discontinuous on the reals. But it is continuous. Let's go say. But it is continuous. And I don't want to confuse you, but it is going to be that it is continuous on wherever it does exist. It is continuous on its domain. So for wherever it does exist, it is continuous on wherever it does exist, but it is discontinuous on the reals because it won't be continuous there at x equals 0. This is not fixable. This will be always discontinuous on the reals. Where, yeah, let's go like that. Is this at x equals 0? If we say at a point, see, for example, if I say this is x is whatever this number is, at x equal to 5, it is 5. We can fix it at x equal to 5 by just bubbling it in or defining it. Then that makes it continuous. But there is no way you can fix this at all ever. This is not fixable, non-removable. This one right here, these are called jump discontinuity right here. It has a jump discontinuity at x equal to 0. You want to say here x equal to 0? It has a jump discontinuity. And if I, whatever this number is, at x equal, whatever that number is, x equal to like 3, I don't know, I'll make up for it. Is it 2? X equal to 2. At x equal to 2, another jump discontinuity there. This is called a jump discontinuity. Not fixable. Also, this is not fixable. It's not removable. Why? Because if you try to make it continuous, well, then it wouldn't be a function anymore. But if I try to connect them, like this and connect them like this, or this particular one here, for sure, then they wouldn't be a function anymore. Because for the input of 0, you got an infinite amount of outputs. It wouldn't be a function. That's a jump discontinuity. So, non-removable. All right, let's move on to, so let's understand that these three types of discontinuities. Let's move on. This is called 1.10 limit of composite functions. We're doing two kind of, the other one, yeah, this is the main lesson, 110 also. Limit of composite functions. The limit as x approaches a of f of g of x is equal to f of the limit as x approaches a of g of x. But this would only be true if you have two continuous functions at x equal to a. Provided that the limit as x approaches a of g of x is L, whatever that limit would be, and that the second, the f function, the outer function, is continuous as well. But if it's not continuous, then we got a problem. F of x has to be continuous at L. All right, consider the graphs of the functions f of x and g of x given below to find the following limits. So go ahead and copy those two down. So you see some jump discontinuities here. And we'll do this problem 1. So I'm just going to assume that this property and this limit, this statement is true. And I hope that it'll be easy to work out. Let's assume that this is true, and we're gonna do then the limit. No, well, we're gonna put the limit inside, so it's gonna be f of lim x approaches 1 of g of x So what is the limit as x approaches 1 of g of x? Limit as x approaches, or use What is Geo? What's the limit as x approaches 1 of g of x? 0 is correct. So we're gonna just go and everything is fine with the statement here. We have no problems. So we can go ahead and just go f of 0. There you go, Brian. What's f of 0? It's not even this limits calculus. It's just simple f of 0. What's the output of 0? What's f of 0? Did you really say 0? Come on. Gio, what's f of 0? 2. F of 0 is 2. I don't know what are you doing? You overthinking? What f of 0? F of 0. This is f. F of 0 is 2. Okay? This is not hard. Well, this is not supposed to be. Just wait till we'll go into the more difficult ones. So f of 0 is 2. The answer is 2. All right. So nothing broke down. Everything here was simple. Is okay. So now let's do one that is more difficult. Yeah, that doesn't follow this. Let's go with number 2. So for problem number 2, we're just going to still go ahead and put the limit inside and go g of lim x approaches 0 of f of x okay. So what is that? Anybody, let's go. What's the limit as x approaches 0 of f of x? Huh? It's 2, isn't it? The limit as x approaches 0 of f of x, limit x approaches 0 of f of x, as we get closer and closer, the limit also is 2. So the limit is 2. So, okay, good. So we're good. So now we're going to go to g of 2. Yeah, g of 2. Because the limit as x approaches 0 of f of x is 2. So what's happening here at for g of 2? G of 2. What's happening here? What's going on at 2? It has what? What is this called? A jump discontinuity. And we got a problem. So why do we have a problem? Because this statement is true. This is no problem whatsoever. So this is the problem. F, or the output. Not necessarily, see they're saying F, no. The outer function. This should say, provided that the limit as x approaches a of the inner function is L, then the outer function has to be continuous. What I mean by outer function is this. This is outer. And for this F, well, this is outer. Okay? This one fitted exactly what is F. So it's the outer function. And the outer function is not continuous. We got a problem. Okay. So now, we cannot follow this really. The law, this statement does not work here. All right. Watch. Now, really got to understand now this. We got to work more. So basically, this is what we're going to do. G of lim x approaches 0 of f of x. Okay, you have to understand. So the limit as x approaches 0, lim x approaches 0 of f of x. So it's coming from the bottom, from the left. See, all this, here, these outputs will become inputs for G. So that these outputs become inputs for the other one. So these outputs are getting bigger. See, the output is say half, then it's 1, then it's 1.5, 1.9, and like that. So they're going, so these become the inputs for here. And so that'll be coming from the right. Let's see. Let's see. No. These inputs, yeah, so it's coming from the left. So hold on here. It's coming from the bottom. It's coming from the bottom. So on the number line, okay, I messed it up. So here, they say this is 2, no? This is 2. So we're coming from the bottom. So this is 0, then it's 1, 2, 3, 1.5, 1.9. So we're coming from the left. So we're going to be coming from the left here. So from the left, the limit is going to be coming from the left. So if it's at the bottom, it's coming from the left. So what is the limit here? It becomes a one-sided limit. We don't even care about the right side. So what's the limit coming from the left? What's the limit coming from the left? It doesn't matter if it's defined here. It doesn't matter. It's not defined. It doesn't matter. The limit will be what? 3. That's it. So it does become kind of a one-sided limit at the end of the day. So the answer was 3. Let's go. Let's see if you understood what I just did. Why don't you take a look at the graph just quickly and figure out if you understood what I was trying to explain here. Let's see if you can do it. Look at the graph. Gio, what's the limit as x approaches 0 of f of x?
0.
Lim x approaches 0 of f of x is 0. Yes. Okay. So we got everything's good, everything's fine. We're gonna go to g of 0, which is the outer function. Better yet, I'm talking about the outer function. So g of 0, that's g. Do we have a problem? It is discontinuous. We cannot follow that one statement. It becomes a one-sided limit. That's if it becomes a one-sided limit. So now, look. Coming from the top, it's coming from both sides. It's coming from the outputs getting smaller. The outputs are getting smaller. And from here, the outputs, what I'm talking about, the y values, it's getting smaller. It's going 5, 4 as we get closer here. So on the number line, as we get closer to 0, we're coming from the right because the numbers are getting smaller. 5, 4, 3, 2, getting smaller. So whenever you're coming from the top, from both left and right, it's because you're coming from the right. Okay, it becomes a one-sided limit. From the right now. So what's the limit? We're coming from the right. because it's coming from the top. So what's the limit? It became one-sided limit. It became this limit. What's the answer? 2. Understood? That makes sense? The answer is 2. Let's go to number 4. The limit as x approaches 0 of sine 1 over x is equal to what? And in order to figure out what this is right here, we have to check what is the limit as we get to 0 from the left and then from the right, and see if they are the same. Same limits. And we're going to apply, this is composition of functions as well. We got sine function, and then inside of it, the outer function is sine, the inner function is rational function. It's the weird one. See, 1 over x, if I was sine x, look, this is what we got. If I could show it to you. We got sine function, which is the outer function. This is the sine function. On and on and on, whatever. This is sine. Y equals sine x. And this is y equals 1 over x. You want to call it just y equals 1 over x. Y equals 1 over x, that's the one we just did. And that one goes like this. And it has the asymptote. And it will never cross, and so it has that asymptote here. So you got, this is the inner function. This is the inner function, and then sine x, the outer function. Well, let's still apply that rule. Let's plug it in there. So we're going to go sine of 1 over sine limit x approaches 0 from the left of 1 over x. So we got a one-sided limit here for this thing here. Okay. What do Gio? What is the limit as x approaches 0 from the left of 1 over x? What's the limit as x approaches 0 from the left of 1 over x? Limit as x approaches 0 from the left. Just this. Don't worry about sign. I'm talking about this. What's the limit as x approaches 0 from the left of 1 over x? Anybody want to guess? Anybody want to guess what it'd be? Look at the graph. Look at the graph. Come on, just look at the graph. As I get closer, this is 1 over x. I told you this is 1 over x. As I get closer and closer to 0, what's the limit? Negative infinity, isn't it? Yes or no? Yes? So, negative infinity. So we're going to have sine of some negative big number. Negative infinity. If we could even do that. Sine over negative infinity makes even no sense to me to say that. Because the inputs, these outputs of this become the inputs for sine. And that's just a negative big number. But the problem is that when you plug in a sine of some negative number, as I keep going now here, this x, as I keep going to the left and to the left to the left, what is the sine function doing? Forever is doing what? What is the sine function always doing? It's always going up and down, oscillating. So no matter where you go to negative infinity, as you go to negative infinity, it doesn't matter because it's always going to be going up and down, up and down, and up and down. It doesn't have a limit. This doesn't have a limit. And even if I do it here for this one, and I go lim as x approaches 0 from the positive side of 1 over x, and then I got sine x, I get sine of that thing here, and the limit as x approaches 0 from the right of 1 over x, well, the limit is going to be what? From the right, what's the limit here? Positive infinity. So now I'm going to the right. These outputs of it are becoming inputs for sine. But it doesn't matter because that thing is going forever up and down again. So what's the answer to this? Well, limit as approaches 0 from the left. It oscillates from -1 to 1. It's always, so as input values approach 0 from the left, that thing is always going, it's oscillating. As we approach from the right, it is also oscillating. So the limit as x approaches 0 of sine 1 over x does not exist. The answer is does not exist. So the limit as x approaches 0 of sine 1 over x does not exist. Limit as x approaches 0 from the right of sine of 1 over x does not exist. And even for this one, even more so does not exist. And this is what it looks like. So this is what this actual function looks like. Sine 1 over x is going like this. And then the closer it gets to 0, it's just going to be going like this. Up and down, that's what it's doing. And coming from the right, what closer you get here, it starts oscillating, and then that's all it's doing, oscillating. So the limit doesn't exist. This is rare case. This is the third case of a limit that does not exist. It's an oscillating limit. Yeah, I don't think you'll see this on the AP or anything. Oh, you're not even in AP. All right.